In this video, I'm going to talk about the biosynthesis of niacin, otherwise known as vitamin B3. So this is the niacin molecule, and the precursor to that is tryptophan, which is an amino acid. And so if we go over to this image here, which is a little more detail, we start with L-tryptophan, L just being the stereochemistry of it. Then this enzyme here, which is called indolamine 2,3-dioxygenase, that's what the IDO stands for, that generates this N-L-formal kynurenine. And so the N-formal is just talking about this group right here that is being generated after this ring here is broken. And then we have this formamidase here, which removes formic acid. So it's removing this right here. Turn that to black. So it's removing this right here. So that's just that aldehyde group. And so we end up with kynurenine. And then this kynurenine 3 monooxygenase is going to use oxygen. And with that, it's actually going to add this hydroxyl group down here. And then this kynurenase here, using PLP, which is vitamin B6, is going to remove this right here, while also adding this carboxylic acid here. Then this 3-hydroxyanthranilic acid 3,4-dioxygenase, or HAAO, is going to split the ring open, and then once the ring is open, there is this this non-enzymatic ring closing. But we see here that what happens is this nitrogen now ends up in the ring right there, and we end up with 2 carboxylic acids on the outside of the ring here. And then this, and I'll get into this a little bit later, this is kind of where things get a little confusing. This shows this nicotinic acid down here, which is the vitamin B3. And as you can see, there's no arrow going from anywhere to this. It's just this coming into here. And like I said, I'll go through the confusion of this here near the end of the video. But let's just get started here at the very beginning with this indolamine 2,3-dioxygenase. And so that is this right here. So it's using iron, which is actually in a heme group, same as with hemoglobin. And so this paper shows these 2 possible different reaction mechanisms here. Their model is this one on A, and in the paper they rule out this B pathway here. So I'll just go through the A. And so we have the oxygen that's bound to the iron in the heme there, just like it would be in hemoglobin. And then we have our tryptophan here come in with its 5-member ring oriented towards the oxygen here. And so the double bond in this is going to, the electrons in that double bond are going to move towards this oxygen, while the double bond in the oxygen electrons move down here. And so then this oxygen, well, this could maybe show the electrons moving towards that hydrogen instead. Then the electrons from the binding the hydrogen to the nitrogen move onto the ring. So we end up with this intermediate here, where this carbon is now bound to this oxygen. This oxygen is now bound to the hydrogen that was on the tryptophan nitrogen, and this double bond has moved over to the nitrogen. And now it shows the electrons from this oxygen-hydrogen bond moving up towards this carbon right here, the double bond electrons moving onto the nitrogen. So we end up with this intermediate here, this dioxetane, and then the oxygens actually split apart, which is so two oxygens bound together is a peroxide, and peroxides split apart. That's what they do. Uh, yeah, that's one of the peroxides tend to split apart. So we end up with this that now has these two double bound oxygens on it. And this shows that well, I think that moves into the next step. So all we wanted to get here was this N-formal Kynurenine, and this is the structure for that. So we see it has these two subunits. Then if we zoom in here, this yellow ring structure is the heme group with the iron here right in the center of it. And we can see that that is brought in close to that carbon on the 5-member ring of the tryptophan here in green. I have a measurement here for, it says 4 angstroms, but there would also be an oxygen between here, and so that oxygen would actually be getting even closer to that ring. And so we can see how that would actually be reacting with that tryptophan there. We can see that the heme is held in place by this histidine down here, which is bound, which is complexed with that iron right there. We can also see things like this arginine down here, which is a positively charged residue next to this carboxylic acid on the heme here. And so that's negatively charged. So we can see how that could be helping to hold that in there. And we kind of have sort of the same thing maybe going on up here with this carboxylic acid. I didn't fill in the sticks for the residues here, but it looks like maybe it could even be binding with the backbone on these residues here. Yeah, and so that is the indolamine 2,3 dioxygenase. Indolamine because that's an indolamine ring, and dioxygenase because it's using 2 oxygens. Down here we see that the tryptophan 2,3 dioxygenase, so that has these are the kinetic parameters for it. And so we see that the subunit mass is 34 kilodaltons. The Km is 0.35 millimolar, and so that's something like 35 micromolar. Actually, no, it'd be 350 micromolar. But then the Kcat is 22 turnovers per second. And we see this lists the cofactor, the heme, and iron. All right, and then the next step is this formamidase, and there are actually 2 versions of this. So there is the zinc dependent and the zinc independent. So I'll go through the zinc dependent first here. So here we still have this aldehyde group on it. So that's what I was talking about over here, where this shows the aldehyde group being taken off in this mechanism, but this is what's actually going to the reactant that's actually going to go to the formamidase here. And so we have this water complex to both of these zinc ions here, and it's being deprotonated by this histidine here. And so the water is attacking the aldehyde carbon right there. And so we end up with this here, where this is now bound to that carbon, and it shows that that oxygen, which would be negatively charged because the electrons would go to it, is now coordinated with this zinc here. And then it shows this bond from the nitrogen to the carbon, the electrons from that actually deprotonating that histidine. And so we end up with this product, the formic acid composed of this carbon and 2 oxygens is now coming off of here. And so that is the, excuse me, that is the zinc dependent. And so this here is the structure of the N-formal kynurenine. I put this here, this 2-aminoacetophenone, because in the structure I have, that is actually what they have bound into it. This is an inhibitor of the enzyme. And so if we look at that structure here, we can see in the dark gray here the 2 zinc ions. We can see in purple here, that is the histidine that would be deprotonating the water. So I actually put the waters that they had from the structure into it. That's what these little red spheres are. But I didn't see any pop up right here next to the 2 zinc ions. So there must be some other way they have determined that it is actually a water in there that is being deprotonated. We can see down here, this is our aminoacetophenone right here. And we can see how that is brought in close to these zinc ions. And so if there was a water there, we could see that this purple histidine here might deprotonate it, and then that water could then attack, well, this nitrogen right here, this amine group, is probably similar to where this right here would be sitting. And so we could see how that water would be brought in close to that aldehyde. That would be right there. Yeah, so that is the structure of the zinc dependent. The zinc independent actually uses this catalytic triad that is that you find in quite a few enzymes that that actually break these types of bonds here, these peptide bonds, which is essentially what that is. So the structure, yeah, right here. So this bond right here is essentially a peptide bond. We have a nitrogen bound to a carbon, which is double bound to an oxygen, and so that gives it that that peptide resonance structure where the electrons from this nitrogen can move down there, and those electrons can move up there, and yeah, that gives it that resonance stabilization. And so this catalytic triad is used quite often to break peptide bonds. We can see here they have just sort of a general peptide bond. And in this case, we have the aspartate 244 sort of holding the histidine in place. The histidine 276, which deprotonates the styrene, which can then attack this this partial positive carbon here, and we end up with this covalent intermediate here. And so from there we end up with this tetrahedral intermediate right here, where it's bound to both the serine and this oxygen right here. And then this shows that that what happens is the electrons from this oxygen actually collapse back down here, and the electrons here would actually move to that nitrogen right there. So we end up with this part actually coming off, while this is still bound onto the enzyme. And then this shows that our histidine can then deprotonate a water, which attacks this, and that can then remove this P1 right here, which we have it showing that down here. And so the structure for that I have right here. So we can see our catalytic triad, that's the aspartate that's sort of holding on to the histidine. And down here we actually have our serine covalently bound to this PMSF, which is this phenyl sulfonyl fluoride. And so this is an inhibitor of this is a pretty common inhibitor of these sorts of enzymes, these sorts of peptide degradation enzymes here, often quite used in labs just to make sure that if you're trying to purify a protein that you don't have enzymes in it that are degrading the protein that you are interested in. And so we can see here that this this serine will actually attack that sulfur there and end up with this covalent bond where we lose hydrofluoric acid from it. And so we can see that here where the PMSF is covalently bound to this serine. And that would be similar to how our N-formal kynurenine would actually be bound to it. It would be bound to it on this carbon right here. But it's still similar in that, but instead of binding to a carbon double bound oxygen, it's binding to a sulfur double bound to oxygen. But anyway, that is the mechanism for the Kynurenine formamidase with the metal-independent amidase. All right, and so now we have generated our Kynurenine, which is this species right here. And so the next step in that is going to be what's called Kynurenine 3 monooxygenase. And so in this mechanism, we have our L-kynurenine going into the active site here. So this shows it moving into the active site, and we have this this FAD, this flavin adenine dinucleotide, which we saw in our last video is made from vitamin B2. And so this is involved in redox reactions. So this also shows that there is NADPH, which is also involved in redox reactions and is actually made from niacin, which is what we are talking about right now. And so this NADPH is actually going to give electrons to the FAD, which is actually what's in the active site of the enzyme. And so we can see this is being reduced so that we have this negatively charged nitrogen here, and we now have a hydrogen on this nitrogen here. And so from here, this actually shows that we're bringing oxygen into the active site here, and it's going to bind onto this carbon right here. And so the NADP, which is now oxidized, is released because it has donated its electrons to the FAD. And then we have oxygen move in. And now, similar to that heme, we have our oxygen sort of bound on there as an oxygen bound to oxygen here. And then this shows acting as sort of a concerted mechanism here. The electrons from this hydrogen-nitrogen bond are moving down here. The electrons from this double bond are moving up towards that oxygen there to create a bond with that oxygen, and then the electrons binding this oxygen to the other oxygen are actually moving down to deprotonate this. And so concerted, meaning that this is sort of all happening at once. Where I started talking about it was arbitrary. And so we see now that we've created a bond between this carbon here and this oxygen, and we've broken this bond right here. So we end up with the oxygen bound onto this ring here, and this still bound onto the FAD. And then this shows that a base comes in, deprotonates this carbon here so that the electrons can collapse back down onto this bond, and this carbon double bond to nitrogen then moves over and picks up a hydrogen right here, so that we end up regenerating the aromaticity of this ring while having added this oxygen right here. And then the product, which is the 3-hydroxy L-kynurenine, can now leave the active site. And then this seems to kind of just skip over it, but we do have to get rid of this oxygen right here. And so this seems to just kind of say, well, it's leaving as water, which makes sense. So what's probably happening is maybe this oxygen is attacking hydrogen ion, and the electrons from this nitrogen are collapsing down so that this can leave from there. And so if we look at the structure, well, first this is the L-Kynurenine here. I put this up here because this is the inhibitor that is in the structure I have. And so if we look at that structure here, so we can see in yellow this 3-ring moiety here is from our FAD. We can see here in the active site, this is the inhibitor that they used to get in this structure. But we can see how this aromatic ring would fit into the active site similar to this aromatic ring, and we can see how this this nitrogen right here would likely fit into the same place as this nitrogen right here. We have this double bound oxygen right here would probably fit into the same place in our active site as this oxygen right here. And so in our mechanism, we can see that that we are adding a hydroxyl group that is on the other side of the nitrogen. So that would be to this carbon here, which would be similar to this carbon here on the inhibitor. And so if we look for that carbon there, so that would be, we said it was this carbon right here. Yeah, so I mean, maybe it doesn't fit in exactly like that because this is kind of oriented away from the FAD right here. So this might not be fitting into the active site exactly the way the kynurenine would be fitting into it. But we can see how the FAD is being brought close to where that FAD would be kind of fitting into the active site right there. So the reason I kind of went through all that about this structure here is because that's oftentimes the logic behind an inhibitor, is that it fits similarly into the active site, but it just doesn't react like the actual substrate will react. But this, in the structure, it looks like this carbon is actually being brought closer to the FAD in here, where we can see in this that it is actually this carbon, which is similar to what this carbon is like. Sorry, there was a loud car going by outside. But anyway, well, I'm not going to belabor this point too much. We can see that something similar to the kynurenine would fit in here, brought close to the FAD, and that is what we want from our enzyme. All right, and so the next step is this kynurenase, which now takes our 3-hydroxykynurenine from the last step here, and this pyridoxal phosphate, which is vitamin B6. So I have vitamin B6 shown up here. This is actually sort of flipped 90 degrees around, and you can also see that this aldehyde right here has been replaced with this amide bond right here. So we have formed a shift base to hold it into the active site. So this is forming a shift base with a lysine in the active site. But then we can see that our 3-hydroxykynurenine actually comes in and displaces the lysine and forms its own shift base here with the vitamin B6. So the nitrogen over here on our 3-hydroxykynurenine is replacing that shift base from the lysine there. And then we can see that that this shows that this hydrogen is being deprotonated off of here. The electrons moving down to here to make a double bond with that nitrogen. Then the electrons on this double bond moving down and then sort of moving through the ring structure here to end up on this positively charged nitrogen. And so we end up with this structure down here where the double bond is now from the nitrogen to this carbon rather than the carbon on the vitamin B6 here. And now the vitamin B6 has the double bonds in the ring looking like this. And then this shows that a general base from the enzyme here is actually attacking this carbonyl carbon right here. And this shows as R to keep things simpler, but just remember that that is this carbon right there. And so the electrons move up onto the oxygen there. Then as they move back down, we are breaking this off right here. So this bond is actually breaking, and now we have this red structure actually bound to the enzyme, and this pink structure here is bound to the vitamin B6, which is in the active site. And so then we move down here, and this shows that this is coming off. So it shows with water and a hydrogen ion is coming down. So it would just be sort of a water attacking that carbon right there and breaking it off of that base. And so we end up with our 3-hydroxyanthranilic acid, and then it has to remove this alanine here, and so it's actually going to have the lysine come back and rebond with the vitamin B6. And so this shows hydrogen coming in, and so yeah, it shows a hydrogen coming in, and we have the electrons from this nitrogen moving down, this moving up, this moving up, this moving up here, and so this would actually be binding to this hydrogen here, and that's where that hydrogen comes from. And then the lysine would go through the shift base reaction, so it would be attacking that. And I'm not going to go through that. I went through it in the previous video, but anyway, we end up with the lysine now forming this amide bond here, and this alanine is being released. All right, and so once again here we have the well, this is the vitamin B6. This is the inhibitor that is in the structure. And so for this, we can kind of see how this is also similar to the 3-hydroxykynurenine. This structure here, this is the substrate, and this is the inhibitor up here. So we still have the aromatic ring. We have a hydroxyl, 2 carbons away from this long chain here. And so that's what we have going on right there. And so if we look at the Kynurenase here, so I have in the purplish color here, that is the vitamin B6. And then in the magenta, that's the lysine that's actually forming the shift base with it. And this right here is our, in yellow, is the inhibitor right here. And we can see how that is close in here to this vitamin B6. So this nitrogen would actually be attacking this carbon right here in our mechanism, and so we can see how that is being done. We can also see, how this arginine here, this positive charge, is next to this carboxylic acid, which is negatively charged. So that's holding that in. This phenylalanine is next to the aromatic ring on the vitamin B6. So there's probably some pi stacking going on right there. Yeah, and so we can see how that is fitting uh, into the active site there. And so this phenylalanine here is also doing a different kind of pi stacking with this phenylalanine, with the aromatic rings. And so from there, that was our Kynurenase. And now we end up with this 3-hydroxyanthranilic acid. And the next step is this ring opening that's done with the 3-hydroxyanthranilic acid 3,4-dioxygenase. And so that mechanism I have over here. And so there's actually two sort of proposed mechanisms for this. This one was found in a paper. They were using this QM calculations, which is quantum mechanical calculations. Oftentimes called QM, MM for quantum mechanical, molecular mechanical. I'm going to go through this larger one here. It's just a little bit easier to see. They're a little bit different. We can see that this one has this radical here, where this has it here in the same place, but then this has another radical later on where this one does not. But the mechanisms are very similar. In this case, we have this iron without a heme. It's being held in by these histidines. We have oxygen and our 3-hydroxyanthranilic acid come into the active site. Just like with the heme, the oxygen binds onto the iron, but in this case we have this radical going on where our substrate is coordinating with this iron. Then this shows that the iron is actually taking away an electron from this, and so that's how we end up with our radical here. And then this shows that the radicals from here and from our oxygen are actually going to come together to generate this bond right here. So this is now bound to this oxygen, and these two oxygens are bound to each other. This shows that the ring is actually expanding outwards. And so this is possibly happening so what's probably happening is that one of these bonds is actually moving out to the oxygen right there, so that this oxygen ends up in the ring structure as we see here. And then this shows that this oxygen is now attacking. So this is attacking that carbon right there. These electrons moving up to that oxygen. So we end up with this structure right here. And then what seems to be happening here is that the electrons from so which one is this saying that they're coming from? So for here, it looks like maybe the electrons yeah, it looks like they're moving down from this one. So the electrons are moving down here, and then these electrons are going to move over onto here, which those can then move down to form a double bond there. Those move there, those move there, then those move onto the nitrogen, and that's how we end up with this structure right here. And then this is still coordinated with the iron, but then we have some waters come in to coordinate with the iron, and this 2-amino-3-carboxy mucinate semialdehyde comes off of the enzyme there. So we can see that this is similar. This ends up having this negative and positive charge on here, which we did not have we did not have a negative or positive charge going on this one. And like I said, it has this this radical electron right here, which we did not have a second one going on over here. So this is just some kinetic parameters here. I have these circled or boxed here, but these are the corresponding residues in the human system. And so we can see when they got rid of these arginines or this glutamate here, that this lost quite a bit of activity. Well, the glutamate didn't seem as important, so it actually started binding a little bit tighter, about twofold tighter, but it still lost a bit of activity right there. And we can look at the structure for that right here. And so I have in the bright red here, that's the iron, and then in sort of the salmon color, that is the oxygen that's actually in the active site here. And this is our substrate right there. And we can see the iron is being held in by these histidine residues right here, and this glutamate residue right there, which is what they show over here. So this shows a glutamate and then these two histidines right there. We can see how these oxygens are being brought close to the substrate there, so that it can actually react with the substrate. And in fact, this oxygen here, this hydroxyl group and this amine group, seem to be coordinating with the iron in the bright red there. I have in purple the residues that they mutated for these kinetics here, and it looks like this aspartate is being brought in close to the iron, so that might be coordinating with the iron. It might be coordinating with this histidine here. This arginine here looks like it's coordinating with the oxygen, and so maybe that is what in this mechanism here might be stabilizing this negative charge right here in this part of the mechanism. And this arginine is a little bit further away, but we can see that that might be coordinating with the carboxylic acid on the substrate right there. All right, and so now we've gone from the tryptophan and we've gone to this ring opened structure, and then I have over here in yellow. So we can kind of see the mechanism for how this ring would close, and this is a non-enzymatic ring closing. So the nitrogen here would actually attack that carbon there. The electrons move out onto that. And so we end up with, well, this oxygen is going to be released as water, as we see here. So with this, we end up with a 1, 2, 3, 4, 5, 6 member ring with the nitrogen in it, and then this oxygen will leave as water, and this will be carboxylic acids sticking off of it. And this is quinolinic acid. And so the quinolinic acid is here. We can what's called ribosylate it, adding a ribose group to it. So we can have our ribose 5 phosphate here. Then ATP can actually add a pyrophosphate onto it, leaving AMP. And then this right here, this 5-phosphorybosyl 1 pyrophosphate, can then be added onto this quinolinic acid, and it will be added onto the nitrogen right here, and that will release the pyrophosphate. And this also shows that there is a decarboxylation. And so now we are getting into this territory that I said was kind of confusing. Well, let's first take a look at this structure here. So this is the last structure we have. So this has a zinc in the middle here. We can see our our phosphoribosylpyrophosphate our phosphoribosylpyrophosphate pyrophosphate here, and in cyan, and we can see here in yellow this is our quinolinic acid. And so we can see that this is that this nitrogen is brought in close to this phosphoribosyl pyrophosphate. And, well, this is a phosphoribosyl pyrophosphate analog here, but we can see that there is the phosphates here, which this one right here, so it's adding onto the carbon here in the ring structure right there. So we can see that that is being brought into this carbon right here. So we can see that this nitrogen goes to this carbon here. I'll even put a measurement there. So there to there, about 4.1 angstroms. And so we can see how that substrate is brought close to the phosphoribosyl pyrophosphate. And so, like I said, this gets to this confusion here. So actually, I'll start with this over here. So this is that end of the pathway here. So we had this open ring structure that closes non-enzymatically. And then this was that phosphoribosyl addition here to the quinolinic acid. And this shows that the addition of the ribose and the decarboxylation are happening at the same time. And then we end up with this nicotinic acid mononucleotide. But then we see, so I added these arrows in here. In the reaction, there isn't an arrow moving from there to there. So I've looked at several papers, and I mean, you can see over here, I have two examples of it showing going from the quinolinic acid right here, decarboxylating to this, which is the nicotinic acid. This is the vitamin B3 right here. And this shows the same thing. We have our open ring here. It closes to quinolinic acid, and then it shows just sort of a single step going to the niacin. But I was unable to find any indication of an enzyme that actually does this reaction right here. And so some papers made it seem like maybe there is something that can go right from quinolinic acid to nicotinic acid. I mean, it seems easy enough. It's just a single decarboxylation. An old paper I saw, I think from like the 1960s, actually showed it going from this structure right to nicotinic acid. I don't know how trustworthy that one is. But a lot of papers make it seem like you need to actually go through the nicotinic acid mononucleotide before getting to the nicotinic acid. So that's actually what I have up here. So we see here that our nicotinic acid mononucleotide comes in to this confusing mess here. This is our nicotinic acid mononucleotide right here. And so this can then be turned into nicotinic acid adenine dinucleotide. So then that can be turned into the NAD+, and this is sort of the point of vitamin B3 is to make this is used for redox. And so then it seems like maybe we need to go through this as an intermediate if we even want to get to the nicotinamide, which can then be turned into the nicotinic acid. But see, that's kind of confusing too, because we started with the nicotinic acid. So is there some way to go directly to this, or do we have to go through all of this? It almost seemed like in the literature there was a sort of conspiracy of silence. Like I said, the papers always just showed something like this, like, oh yeah, we get to quinolinic acid, and then And then, something happens, and then we have our vitamin B3. Um, so up here is just another pathway kind of showing the same thing. So we see in a lot of cases these papers would show the nicotinic acid, the niacin, the vitamin B3 as always coming into this pathway here. And then that gets turned into the nicotinamide adenine dinucleotide, the thing that we actually want. This is the cofactor that we're actually trying to get. This is why we need vitamin B3. And then this NAD degradation then goes back to the nicotinamide. So this has the amine on it rather than the carboxylic acid, and only then can we generate the nicotinic acid here. And so it seems to be, so you can even see over here, this shows the nicotinic acid over here and the quinolinic acid over here, and never the twain shall meet in this pathway here. And so, yeah, this is another pathway I found where it shows the tryptophan coming in. The multiple arrows means multiple steps, but then we end up at the nicotinic acid mononucleotide. And only then do we go through these steps to end up at the nicotinamide, which is then converted into the nicotinic acid. And just to kind of make that clear, so nicotinamide and nicotinic acid are not the exact same molecule. So the nicotinic acid will look like this, and then it has a carboxylic acid on it. And the nicotinamide is like this. It still has the aromatic ring, still has that double bound oxygen, but then we have this. And so these can be interconverted pretty easily. So we could have a nitrogen attack this to turn it into this, and we could have a water attack this to turn it into that. So that's it's a pretty easy conversion, and both of these would actually work as vitamin B3. And so you can say that vitamin B3 is both of these molecules, but there is that change between the carboxylic acid and having the nitrogen on there. But yeah, anyway, this, like I said, this seems to show that we need to go through this nicotinic acid mononucleotide step in order to get to the nicotinic acid, which can then sort of be circulated back in to generate more nicotinic acid mononucleotide, which can then be used to generate nicotinamide adenine dinucleotide, which is used for redox reactions. But yeah, that is the vitamin B3, biosynthesis pathway. So this is something I took from Wikipedia. So this also shows that tryptophan can be used to generate serotonin and melatonin. And I'll go through that pathway in later videos when we start getting much more deeply into metabolism. But tryptophan is also used to generate niacin. And from what I've seen in the literature, humans can actually generate niacin. It's just extremely inefficient. I think it was something like you need like 60 milligrams of tryptophan just to make 1 milligram of B3. And so it's very inefficient, even though humans can do it. And so we need to have our niacin needs, our vitamin B3 needs, supplemented in our diet. Yeah, and so that is the biosynthesis of vitamin B3 in the next video. So I don't know much about any vitamin B4, but the next one will be vitamin B5, and make sure to check out my other videos on nutrition. So far, I've only been going through some of the uh, vitamin biosynthetic pathways, but as these videos move on past the biosynthesis of vitamins, we'll start actually getting into human metabolism. And I will see you in the next video.